nanohub.org.
Online simulation and more for nanotechnology.
So first of all, welcome back. This is going to be the last lecture, and so this won't be on the exam, but in some ways this very kind of forward-thinking type of lecture, because it's really talking about like what is the future of optical telecommunications look like in a very broad sense. And so basically my argument today will be that the future is quantum. But like all predictions, you know, this isn't necessarily correct until it's proven out in reality. But I do want to talk about, if quantum networks are the future, what are the principles behind quantum networks, and what are the components that we'll need in that context to make it happen. Okay. So first of all, like just very, very broadly, what is a quantum network? This concept was proposed about a decade ago by Kimball. He's at Caltech. And basically, in a very simple sense, this is very analogous to the optical transport networks that we've grown to know and love over the last few weeks. But you can see there's a key difference, which is just that instead of having classical nodes, which basically are like the nodes in the OTN, or optical transport network, we have quantum nodes. And instead of classical optical channels, we now have quantum channels. But of course, part of the point of this connection between what I'm talking about today and what I've talked about previously is that we can indeed reuse a lot of the same fibers that we already have throughout the world to create like a new quantum network instead. But there are some challenges that I'll talk about. So basically, what is a quantum state? In general, I'm going to assume for the sake of brevity that you know kind of the very fundamentals of quantum, i.e. that you can have these so-called entangled or Schrödinger cat-like states. But I do want to emphasize like what are the specific types of quantum states that can be of relevance in the context of optics. Okay, so usually the way to think about it is that optical quantum states are basically flying qubits. So in other words, you're storing information through the photons themselves, basically choosing entanglement or superposition of states between two or more possibilities within a Hilbert space. Okay. And so, for example, there was a recent review paper from Vukovic's group at Stanford that basically just talks about two examples of how you can get entanglement of photon states. In one case, you basically have two waves that have two different polarizations, horizontal and vertical, okay? And then you basically go through a half wave plate, and then these two previously decoupled states become entangled into superposition of like plus and minus superposition states, okay? And then this just showing like on a Poincare sphere, basically where you are with these qubits. And so the key point is you can take individual modes that are deterministic and then turn them into these superposition states. And then as you may know from quantum mechanics, once you're in superposition state, that means you have a certain probability of measuring each particular outcome when you do measurement, okay? And then another way to do something kind of analogous is you can use a set of polarization beam splitters, and this showing basically you can take these individual states and then basically using the polarizing beam splitter, divide the polarizations and then apply different amplitudes. So you can actually rotate the individual degrees of freedom independently, even when it's in superposition. So then that means that in principle, there are a lot of things you can do. Okay, so in order to basically like have full control over the quantum states, now you can't just directly use light to control light. You must usually couple to matter in some way. And so here basically you have a very important concept, which is kind of called cavity quantum electrodynamics, or cavity QED. And there are basically two regimes that are important. The first is the weak coupling regime. And so basically in the weak coupling regime, that means you have an increase in the rate at which matter emits light. So it's basically a decrease in the spontaneous emission lifetime. And so this phenomenon, where it happens in a cavity, was discovered by Purcell, who happens to be a Purdue graduate, by the way. And in 1940s, he wrote basically a less than one-page paper reporting his results from Harvard. And then he showed that you can actually get a substantial increase in emission in a cavity in radio frequency. But this also applies to optical frequencies as well. And so this optical emission enhancement or decrease in spontaneous emission lifetime also increases stimulated emission rates as well, of course. So this whole phenomenon is called Purcell enhancement. Now, if you go beyond a critical value, though, where basically you're coupling to like the atom from these optical modes at a rate g that's greater than either the rate kappa at which you're coupling in and out of the cavity, or gamma, where you're basically seeing like non-radiative decays, then you get into like the strong coupling regime. And so in the strong coupling regime, then actually there's not like a distinct light state and matter state, but you actually have a superposition of light and matter states. So then that superposition means that you have two slightly separated modes that are basically like plus or minus modes in that superposition. And then that gives rise in turn to Rabi oscillations, where basically the whole mode kind of like oscillates at a so-called Rabi frequency that depends on the intensity of the light that's being applied. Right, so that's the two regimes. And of course, both can be useful in different ways. So it's not that one is better than the other, but they're just different. Just to give you an example, like more concrete of what I'm talking about. So this is showing a Fabry-Perot cavity. And so Fabry-Perot cavity is a chance to use the Purcell effect to substantially increase the coupling rate of individual atoms to the photonic modes that are embedded in the Fabry-Perot cavity. And you can see here, this actually, by optical standards, fairly large, like 10 micron Fabry-Perot cavity. That's the gap. You can see the whole structure is actually on the order of a few millimeters. So it's fairly big, like it's a macro size, actually. So you can take a photo. And then there are other things that can be done as well that are even more interesting than enhancing emission. This is showing actually that in some cases with these quantum networks, you can actually have particular states at a given position, and then you can actually come up with schemes to actually transfer the quantum information without destroying it to another location B. And in a little bit later, I'll explain more about how do you do that. But sometimes it's called like quantum teleportation as well. And then like just to give you an example of how this could work, you can do entanglement using this 50-50 beam splitter, where basically you have two different spatial optical modes, that are called like the left and right mode, basically. And then you have this phenomenon called Hong-Ou-Mandel Interference. So then basically what happens is you have basically four possible paths when two beams come in this direction. And the idea is that basically this mode where basically you reflect here and reflect here, and then the mode where you transmit here and transmit here, these two cancel each other. So that actually creates like a quantum entanglement between like these left and right modes. Initially, these left and right modes may not have anything special happening, but then afterwards, if you have aligned everything correctly and you have exactly the right beam plate, so that basically photons coming from reflection of right or transmission of left are identical. That's really the key criteria. And of course, for here too, reflection here or transmission here are identical and indistinguishable. Then you get like full entanglement. And so theoretically, that means your density matrix is essentially has equal values for all of its entries. And then in this case, like they saw experimentally in this paper, which was published like about a decade ago, that you can actually get fairly close to the ideal in the experiment using the Hong-Ou-Mandel interference phenomenon. By the way, I think, oh yeah, you had a question.
How such a, so that plate can acting as a entangle the two lights in the.
Yeah, exactly. So that's the Hong-Ou-Mandel thing. So maybe the way to explain it is through a diagram, right? So basically, the idea is you have two beams that are coming in basically at equal but opposite angles. Okay, so if we say this theta here, so you always have this to start off with, but then there are four possibilities. Okay, so then I can say number one is basically this is reflected, this reflected. So reflect, reflect. But then we also have another mode where you start off in the same way, but you transmit and transmit. So then this is double T, okay. And of course the angles are all preserved. This is all in free space. But the key thing here is that these two modes, 1 and 2, reflect, reflect, and transmit, transmit, they can have equal but opposite phases because there is a different phase shift on transmission than reflection, but otherwise identical. So that means that actually these two cancel and then these two cancel. So that means the overall amplitude of these two processes combined is 0. So then the only ones that basically survive are going to be entangled states. So then you basically get two states out of this Hong-Ou-Mandel experiment, one of which is essentially like reflection plus transmission, and then the other one is basically like reflection minus transmission. So it's basically like a superposition with a normalization, like 1 over root 2, I guess. So that's basically the set of states that are coming out of the system.
What I know of the quantum entanglement happens from the same source but at different phases. In this case, is it possible to using a different source?
Well, so the key thing here is that the two paths have to be indistinguishable. So these left and right rays, the easiest way to get both of them is obviously start with a common source, right? So it could be that you initially had something like this, it's just a single laser, and then you're focusing it down like this, maybe. I mean, there are actually many ways you could configure it, so I don't want to say what's the best way because that's more an experimental question.
And then such a plate can be whatever the 50-50 beam splitter will be.
Yeah, so if you get it into the right configuration, then this 50-50 beam splitter should be able to cause interference between like kind of these two simple modes and just leave you with these quantum interference modes. So then that's how you get like that full off-diagonal set of values for the density matrix. Sure, yeah, thanks for your question. You had a question? You mean here? Oh, okay. I think that's just showing that there's no density matrix values experimentally at those positions.
And they are simulating it not the way I was doing, right? They are doing it based on beat by beat.
Well, they're trying to look at the overall quantum state of both photons, but there's no other degree of freedom. So they're just looking at the quantum degrees of freedom for the two photons exclusively, like at the detectors D1 and D2, essentially. That makes sense.
Yeah. So I'm asking a question because in the second one, some two of them are increased, like they are same. So that means that one is 1, 0 and 0, 1. Okay.
Makes sense. Okay, cool. And then there's another thing you can try to do that's even more ambitious, which is essentially if you have a given quantum state A, then the idea is can you essentially take, say you have like 2 quantum degrees of freedom, can you basically send one to node B and then another to node C, right? So this is kind of roughly in the spirit, as we talked about before in the classical case, of taking a multi-wavelength channel and then splitting it with wavelength division multiplexing and then rerouting each wavelength to a different location, right? So that's basically a component we talked about in classical context. Now the question is, can you do this in a quantum context instead? Now this is very hard though. So all I can say is that first you have to do the first thing that we were talking about before you can do this, to actually, divide the degrees of freedom in an arbitrary way. But at least in principle, this is very useful because this gives you much more flexibility, as we know from the classical case. So any other questions now before we move on? Okay, so those are good questions. So now I'll try to explain some of the more recent work as well as some specific components that could really play a role. Okay, so for quantum repeaters, so the reason why this is important is because you have exponential loss in optical networks. So if you have flying qubits, but your loss goes e to the minus alpha L, once L gets large enough, your probability of having a successful quantum key distribution event is really low. And so it's been estimated by several researchers that if you had a 1,000-kilometer optical fiber, then it could take years to exchange one quantum bit, right? Which is pretty slow. So we need to basically have something to solve that. And I think most people think the solution is to have quantum repeaters. And so in analogy with our classical repeaters, the idea is how can you basically amplify the strength of the quantum state so you don't lose it during the long haul transmission. Okay, and so this is actually showing kind of the fundamental concept of quantum repeaters. So it's essentially that you can have multiple Bell measurements to actually check entanglement over local scales. So then rather than trying to initially go all the way from A to B, you actually have these intermediate nodes, C1, C2, C3, that basically allow you to perform a series of Bell inequality measurements to actually see if you can maintain entanglement between pairs of locations. And furthermore, you can actually have cluster states where you actually have multiple Bell inequality measurements at the same time. And so the idea here, in some sense, is you're kind of multiplexing the Bell inequality measurement. So you basically speed everything up by a factor of n, where n is essentially the number of Bell measurements you can perform at once. So if you can basically have n Bell measurements between A and C1, C1 and C2, C2 and C3, and so on, then it becomes much more likely that you can actually exchange entangled states all the way down the line from A to B, right? Because A and B, by hypothesis, are far away, but C1, C2, and C3 hopefully are close enough. You have reasonable chance of success there, right? So this is essentially a way to work around the loss mechanism by adding additional entangled states. And you can even go a little further to actually, try to, create these large networks where you basically have a whole series of so-called cluster states, or basically clusters of individual entangled quantum states that are kind of arranged in a somewhat hierarchical structure. And then these hierarchical structures allow you to now create what's called a final cluster here that allows you to look at more possible sets of entangled pairs than if you're just trying to do direct pairwise comparison between arbitrary set of pairs. But it's more efficient because the total number of operations is lower. So that's really the rationale for doing that. And then if you look at what the impact is of this approach, so basically if we did nothing, then this y-axis is showing you the secret keys that can be exchanged per mode. Then you have this dotted line. And so you can see that once you get it to above a few hundred kilometers, the probability of exchange that's successful becomes less than 1 in a million after about 300 kilometers. Less than 1 in a billion after 500, right? So it goes down quite a lot. But if you actually start implementing some of these repeater algorithms, now you can actually get the chances to be substantially higher for longer distances, especially above 100 kilometers. And so most demos that have been done to date are less than or equal to 100 kilometers, but then beyond 100, then you really may be motivated to use quantum repeater technology. And another variation on this is to use a purely photonic structure where basically all of the Bell inequality measurements are done with photons. So then that makes it, of course, easier to implement in optical fibers. But then obviously there are other challenges such as can you do rapid Bell measurements? Because this graph previously, this was just showing probability of success for each operation, but doesn't necessarily say how fast you can do all the operations. So this is a relatively recent paper a few years ago that kind of explains the concept in detail. Another approach that actually became very widely publicized, I think, last year was satellite links. And so this concept was devised about 5 years ago, to my knowledge. So basically, this paper published on Archive kind of lays out the concept. The idea here is just to take advantage of the fact that once you get into the upper atmospheres, particularly at certain wavelengths, it's very transparent. So then you can essentially take your quantum states, bounce them off a satellite, and then send them to some faraway recipient. And so potentially this recipient may be much further away than it would work for fiber optic communications, right? And I realize that technically this is not fiber optic communications like the name of the class, but I just thought you should know that this also exists. And also there's a comparison here of like what happens in the satellite case versus the quantum state. So basically what this is just showing is that once you start talking about like extremely large ground distances, then there are potential advantages to the satellite-based links. However, if you're talking about these shorter distances, it's not as clear if it's a big improvement, especially below 5,000. There's not nearly as much of an innate advantage. So I don't think there's actually even been a demo for 5,000 kilometer separated satellites or ground nodes from the satellites. Like I think it was like on the order of 1,000 kilometers. And I think what was demonstrated was basically like a bit rate of like 1 quantum bit per second or something, right? So that was obviously important because it shows that this works, but it's not necessarily fast enough for like a practical application. So certainly more work would be needed here, and also it would need to be much longer range for it to be really compelling. Okay, so any questions about the repeaters? Right. Okay. So now let me talk about quantum teleportation. So this is one of those concepts that oftentimes gets confused with science fiction, I should say. But basically, it's a real thing, first of all. I want to emphasize this is really a scientific thing. But let me try to explain briefly what is happening here. So the idea is that Alice has some sort of entangled state, and then she wants to send it to Bob. Okay, so that's really the concept. Okay, so the way to look at this, this is a fairly nice review paper that kind of explains the concepts very broadly. But you have an input state, and then you basically can entangle that state into something that Alice and Bob can actually share. And the way that you do that is first you perform a Bell inequality measurement between the input state and the entangled state. And then you also communicate the results of this Bell detection through a classical channel to Bob. And then this allows you to now output a state at Bob's node. And so in other words, what that means is through this series of measurements, you could take the quantum state that Alice had prepared and then move it over to Bob. Now the catch is like because there's a no cloning theorem, you can't take the state that Alice had and keep it and copy it. You can't just like make your own copy and then send it to Bob. You must send the original essentially. So the original is destroyed during this process, but then in exchange you get the quantum state at the location of Bob. And the key thing here is just that it's not like the same as classical state, because classical state you can always copy, no problem. As you know, like for cutting, pasting, emails or whatever, like you always see like they get forwarded to other people. But in this case, like once you forward this to Bob, then only Bob has it, right? So that's a very key point. And of course, if you measured it before you send it to Bob, you would destroy the entanglement in the quantum state. So therefore, Bob would not be able to get any quantum state as a result. You had a question?
If classical communication system can handle such a quantum phase, from Alice to Bob.
Yeah, I would say there's essentially like two things that are happening in parallel, right? So there's like this quantum communication that's happening to allow you to do the Bell inequality, as well as like transmission of a conditional unitary operation. So that's what's happening here. So all these dark lines are basically quantum links or quantum channels. But then this dotted line is basically the classical channel. With that said, I mean, strictly speaking, like the classical and quantum communication channels could be on the same physical hardware, right? But you do need to make sure they're not directly the same somehow. Like, for example, use different wavelengths, perhaps different detectors or sources as well. But you could still potentially leverage all the fiber optic networks to do both parts of this operation. Now, I'll show you in a few minutes, there's a few examples of doing this with real hardware. Okay, so basically the first example I want to show you is from China. So this is basically showing that you can transmit a quantum state over this lake in China. I wish I remembered the name of the lake, but it's between Gangcha and Guangjing. Sorry. And so basically what's happening here is that Alice is preparing a quantum state, and then she has both a classical and a quantum communication channel with Bob, who's here in Guangjing. And then basically she's feeding this information into Charlie and then implementing the algorithm we just saw a minute ago in order to communicate the information to Bob and basically reproduce the quantum state. So in other words, she's first taking classical state, then preparing quantum state through entanglement. That's basically what all these mirrors are doing, using like a Hong-Ou-Mandel type phenomenon, I believe. And then once it has that quantum state, then doing the Bell inequality measurement with respect to Bob. And then that creates an entangled state between Alice and Bob. She communicates classical information to Bob. And then once Bob receives it, then he records that. And then she sends a conditional unitary state again through a quantum channel. And then Bob reproduces the classical state by combining what he knows about the Bell inequality plus the conditional unitary transformation. And so this was published in Nature a few years ago. So at least it's been shown, like for just a single quantum degree of freedom, this can be done over fairly long distance, like 97 kilometers. And then the year after, there was a demonstration at 143 kilometers. So this was basically between two islands. I think these are in the Atlantic, like La Palma and Tenerife. And so this basically trying to just implement a really similar concept using a classical feed-forward channel for the classical degree of freedom. So there's a slight difference in the classical degree of freedom, but it doesn't really change things too much. So I won't re-explain it too much. Now, that's not the only thing that's been done. There's also been like these tabletop experiments showing that in addition to doing what we just talked about, you can also essentially implement the same kind of algorithm with a combination of quantum and classical channels between Alice and Bob using this kind of setup where essentially you have like a set of heterodyne receivers on Alice's side, and then basically you have the entanglement and quantum channel which exists here between Alice and Bob. And then you also have the classical communication channel. And the classical communication channel now modulates these electro-optic modulators through a series of mirrors in order to basically give you a final heterodyne detection, which basically allows you to see if you successfully transmitted the quantum state of the system. Now the catch is this is much shorter distance than the previous examples, which were like hundreds of kilometers. But I think this can also do perhaps more quantum states at a time. But basically the point is there are a few variations on this same concept that have been explored. And just to compare the performance, you can see for photonic qubits, in these like 143 kilometer systems, the efficiency is less than 50%, but that's still pretty good given how new the technology is. And the fidelity, or basically the accuracy of reproducing the original quantum state, is around 83%. And then if you look at the tabletop experiments I was talking about just a minute ago, the efficiency is actually very high. It's close to 100%. And the fidelity is comparable. So, of course, it's over a much shorter distance, so arguably it's not a fair comparison, but it is more efficient. So, any questions about this part? Quantum teleportation. I know it sounds like really bizarre concept in some sense, but it does work. But now this brings me to the last topic I wanted to talk about, which is quantum computation. Okay, so I see most of you heard of quantum computation. So as you may know, the concept of quantum computation is to take advantage of very large Hilbert spaces. And so in particular, as you know, if you have a quantum bit, you essentially have a Poincare or block sphere where you can have all the possible states. And so that's like, maybe you could think of it as like maybe a few different states. However, once you get to like a larger number of qubits, then with entanglement, actually the number of possible Hilbert spaces or states grows exponentially. So it's not like a classical system where you have twice as much information stored with twice as many bits. Now you have exponentially more when you double it every time, right? So then it basically scales like very rapidly in principle. Okay, and so the classic example that a lot of people have heard of is Shor's algorithm. Shor's algorithm, the concept is very simple, which is that you take a large number and then you're trying to factorize it. So this is actually related to the RSA problem that I talked about Wednesday. And so in RSA algorithm, the key thing that's hard to solve classically is factorization of a product of two large primes. But here, basically, the way Shor's algorithm works, I mean, obviously I'm oversimplifying a little bit, but it's essentially looking in parallel at all the possible factorizations. And so now what would have taken basically like an exponentially long time now takes polynomial time. And so there's an exponential speed up. So this in some way is solving like these so-called NP hard problems in principle, at least one of them, right? And so that obviously shows how powerful quantum computation can be. At the same time, there are a lot of practical challenges, such as how do you prepare like essentially arbitrary quantum states like with exponential number of degrees of freedom and then make them insulated from noise or interference. And then this was demonstrated, though, I should say, although I'm not showing you the slide, but Ike Chuang from MIT demonstrated using NMR, you can actually implement Shor's algorithm and get factorization of numbers like, say, 15 into 3 and 5, like using Shor's algorithm. Now, obviously, it's such a small number of qubits, it doesn't sound very exciting. But the point is, like, you can very quickly go from something like factorizing 15 to factorizing something like with 30 or 60 bits of information. And there's been a big push recently to go for what's called quantum supremacy now. So this is a big buzzword. And in quantum supremacy, the idea is just that you'll go from a situation where classical computers have much more computational power to one where quantum computers, even if you just have a couple, will have more power overall than classical computation, even if you have like many, many more, because of this exponential scaling. So in principle, we could be close to this crossover point where you go from relying predominantly on classical computation to quantum computation, in principle, right? So how do you do quantum computation? Obviously, there are a lot of ideas, right? So I'm just going to try to cover some of the optics related approaches because of brevity, and also that's what's related to the class. So basically, the easiest thing to think about actually for quantum computation is called a conditional NOT or C-NOT gate. And so in the CNOT gate, the idea is you first create an entangled state using a beam splitter. So that's analogous to the Hong-Ou-Mandel experiment. But now you also have a nonlinear phase shift, so that if a single photon actually passes through one arm, it gets a different phase shift than if it goes through the other arm. And so this allows you to now perform logic gating on your quantum states, entangled states. Okay. So in principle, that's amazing. Let's do it all in optics, and then we'll have like so much better computational power than we have now. But there is a catch, obviously, which is that the nonlinearity has to significantly shift the phase at a single photon power level. And of course, as you may know, nonlinearities are not usually very strong, like say Kerr nonlinearities, they're very weak. So then if you just put a single photon through that nonlinearity, even for a fairly long length, basically it has very low probability to interact. So the phase shift is basically 0. So that doesn't really do anything. So then you need to actually enhance the nonlinear interaction somehow, but at the same time not to absorb the photon. And that's really where it gets hard. So I already kind of talked about the Hong-Ou-Mandel interference. And so basically you can think of this as like kind of the very early stage version of the CNOT gate, but really limited by this nonlinearity. It's just showing like how the interference effect that I was showing you earlier is working, right? So this is fairly similar to what we talked about, but you're really constrained by this nonlinearity. So more recent work actually has tried to do what are called cluster states. Okay, so then the cluster states that I had been alluding to earlier, here are the ideas that you actually have essentially like multiple entanglement events. So maybe you start with initial wave function, and then you actually have transformations on the wave function to connect it with other states in the system. And so the idea is basically you have a series of gates that will cause entanglement. And so the whole point of this, or reason why people are interested, is because this is a way potentially to overcome the weak nonlinearities without introducing absorption, because you're basically saying, like, okay, each of the arms that we had before, maybe it creates a very small phase shift. But if we can get even a tiny phase shift and we have enough of these operations and they're low loss, then we can basically string them together to get something that actually is a meaningful amount of entanglement. And so the kind of the net result is you take this psi here and then you multiply it by a bunch of unitary operations to get the final state, like psi prime, if you will, right? And so here it's just shown for like 3 operations, okay, just for simplicity, but you're certainly not limited to 3. In principle, if this is low loss enough, you can do as many as you want. And so maybe instead of 3, you could do like 30 or even like 300 if needed, so that you have enough entanglement events, so that you have, like, at the end of the day, a highly entangled state. And so another way to call this kind of clustering approach is multipartite entanglement. And so the concept in some sense is very simple, but it's just a way to overcome the inherently weak nonlinearities in optical systems. However, another thing that's very complementary to this is to also go back to what we showed earlier, where you have, like in the weak coupling regime, you have Purcell enhancement. So you can potentially combine Purcell enhancement and multipartite entanglement in cluster states so that each unitary operation is stronger, but you also have more of the unitary operations. So now you can actually have a substantial rotation of the quantum state, which is needed usually to do quantum digital logic, essentially. And then there are a lot of other things that need to be accounted for in these kind of systems, right? So of course, like there's the fact that the wave function itself will decohere after a certain amount of time. So you can't put it through like extremely long distance in order to do the entanglement, or otherwise you'll lose your entangled information by the time you're done. And so typically there's a concept of what's called gating time. And so you can think of like the path that this has to take is setting a length L. And so then if you have basically everything's traveling at a speed of light c/n in some medium n, then basically L divided by C over N, or NL over C, is basically setting characteristic timescale for this problem. And so that's like our gating time in this multipartite entanglement. So let me write this on the board. Okay, so if we say there's a gating time, which is essentially L, the total length, divided by C over N. Then there's also coherence time. Okay, and so then we could call this tau coherence. Okay, and there are two types of decoherence that can take place. So first of all, there's losses basically from emission, and so we can call that a T1. So that's basically the rate at which you're emitting photons, or photons are basically being absorbed by atoms, and you're basically losing the quantum information. But then there's also this so-called T2 lifetime, and then the T2 is associated with essentially operations where you have like rotation of the Bloch sphere, but you don't have a loss of energy, but it still can wipe out coherence in the system. And so this total coherence time is dictated by the sum of the rates of losses and decoherence processes, such as phonon scattering, right? So this is loss, and this is scattering, essentially. So that means that you need something with very low scattering and also very low parasitic losses. And so if you have that, then basically your goal would be to have this coherence time, tau, as I called it, to be much greater than this gating time, delta t. Okay, so if you can achieve that, then you have like a viable quantum system. And this should, in principle, have like very high fidelity, or otherwise, in other words, like a high probability of success. But with that said, there's still one other issue, which is essentially, even if you have a good quantum fidelity, if it's not one, like what do you do? And so then there's also this concept of quantum error correction, where basically if fidelity is above a certain value, you build in some redundancy into the algorithm so that you can correct for errors that may take place during the operation, right? And so that's also a very interesting topic in its own. Unfortunately, because of time constraints, I didn't have enough time to really go through that in detail. But I can send you papers if you're interested. Just let me know. Like Mabuchi had worked on that among other people. So, sum up, I think we covered a very broad range of topics, right? So it's all about communications in some sense. And we started with essentially the history, like telegram cables, getting into kind of like the early work on fiber optics, just realizing that you can transmit light over fiber, and that might have higher bandwidth than copper. And then basically like ramping that up basically with like just single frequencies, using like very simple encoding schemes. And then we went to the modern WDM networks, in which you have like very sophisticated ways of dividing up wavelengths, dividing up time, code, and then basically like slicing and dicing all the input wavelengths in the optical transport networks, basically to send different wavelengths in different directions for different purposes and to dynamically reroute them, but then also to connect with all the things that we use every day, such as Wi-Fi and cell networks as well, right? So there's a lot of interesting stuff happening already. And of course, we also looked at the future, and part of that is going to be an extension of the classical approaches that we already know. So basically going to narrower division between modes and wavelength division multiplexing, and then higher number of symbols in digital signal processing encoding. But it also looks like there's going to be a move to quantum channels as well, and quantum networks. And these quantum technologies will transform a lot of things, like particularly in regards to privacy by ensuring much better privacy than we have now, but also potentially unlocking the ability to do exponentially more communication and computation than we can do now. So a lot of really amazing and unexpected to the vast majority of public things could start happening in the next decade or two. So it's a good time to get involved in this area. So thank you. Thank you.
Thank you for taking this class and summarizing some really important papers.
Yeah, my pleasure.
I have a tendency to read and then forget about it and then thinking about it. I have somewhere now to.
Yeah, and I definitely would recommend if you have time to read all the papers I reference, because they're all like nice papers actually. So, I mean, it's up to you obviously, but I would say if you want to pick one, then you should start with Kimball's paper, because that really kind of lays the foundation for what a lot of people are working on today.